Hey guys, and welcome to the video. Today I will talk about how you can implement a custom optimizer in PyTorch. I'm on the official GitHub repository of PyTorch, and I'm going to show you where exactly you can find the relevant source code for implementing custom optimizers. The module we're interested in is under the subpackage optim and is called optimizer.py. And here we have a class called optimizer that is supposed to be subclassed each time we want to implement a custom optimizer. As you can see, the constructor has two arguments. One is params and the second one is defaults. The params argument is an iterable, and there are two possibilities when it comes to the elements. First of all, one can just have an iterable of tensors, or one can provide an iterable of dictionaries. So if we decide to go for an iterable of tensors, we can only have one set of hyperparameters for all of the parameters. However, if we decide to go for an iterable of dictionaries, we can specify different hyperparameters for different parameter groups. Let us now focus on what is inside of the constructor. As you can see, we define two different attributes. First of them is state, which is a default dictionary, and the second one is going to be param groups equal to an empty list. The state attribute is really useful because it allows us to store any information and then use it in future steps. One specific example of when the state might be useful is when we implement momentum optimizers that need to store information like the parameters from the previous step. The second attribute, param group, serves as a nice way how you can access all your parameter groups with the same formatting of the parameter dictionaries. The rest of the constructor focuses on populating this param groups list. Here we have the zero grad method of the optimizer, and it's supposed to be called just before calling backward or narrow loss. The idea behind it is to set all the gradients of the leaf parameters to zero. And finally, we have the step method that is supposed to be implemented in the child, and this one is supposed to be called just after calling the backward method on the loss. And in the most general terms, the goal of this method is to update all the parameters. And to do this update, one can use a lot of different things and information. Specifically, you probably want to use things like the inner state that we just saw, or the gradients of your parameters. Anyway, I think those are the most important things that you need to know, and let me show you an example. Before I start with the example though, let me quickly introduce the Rosenbrock function. It is a real function of two variables, and it has a unique global minimum at this point. And the reason why we want to use it is because converging to the global minimum is not that easy. I will write an example where I define a custom optimizer, and also I will try to see how this optimizer performs on the Rosenbrock function. And to do that, I will also need to write some visualization code. All right, let's get started. I imported matplotlib to create nice plots and animations. Then I have NumPy and Torch to work with tensors and arrays. And here I imported two already implemented optimizers. One is Atom and the other one is SGD. And I will use them to benchmark our custom optimizer. Finally, I imported TQDM to get progress bars. Let us now implement the Rosenbrock function. First of all, we fix the A and B parameters. Namely, A is set to 1 and B is set to 100. Also, let me point out that the way we wrote this function will allow us to use it both with PyTorch and NumPy. Now we would like to implement a function that runs the optimization given a selected optimizer and its hyperparameters. Okay, so this run optimization function accepts multiple parameters. First of all, we need to provide the XY init that represents the starting point of the optimization algorithm. Here we need to provide the class of the optimizer that will only get instantiated inside of the function. We need to provide the number of iterations. And finally, we can pass any additional keyword arguments, hyperparameters to the optimizer. What this function returns is a path, which is a 2D NumPy array where the rows are different iterations of the optimizer and the columns are the XY coordinates. First of all, we create a tensor, set its value to XY init, and make sure that it requires the gradient. We instantiate an optimizer using the optimizer class and the optimizer keyword arguments. Note that the first argument that we're passing is an iterable of tensors, or namely an iterable of a single tensor. And that means that we are not using the possibility of creating groups. However, in our example, it doesn't really make sense to split up our parameters into multiple groups since we only have parameter space of dimension 2. We initialize the path array and we populate its first row with the initial x and y. We then compute the loss, which is just the value of the Rosenbrock function at a given point, and we compute the gradients by calling the backward method. We take all our gradients and we clip their norm to 1. We do this to guarantee that the gradients are not exploding. And finally, we call the step method of our optimizer, and as discussed, it will update in some way the value of our parameters. At each iteration, we cache the corresponding value of the parameters inside of the path array, and finally we return it. Now we would like to write a function that visualizes paths of different optimizers. To do that, we can create a small animation. Alright, let me go through the arguments. We start with the paths, which is a list of all the different paths representing different optimizers. Then, for each of them, we can specify what color we want to visualize them with. And also we can specify, to have a nice legend, what the name of that optimizer is. Of course, we can also specify the figure size and the X and Y limit of our figure. We return an animation that is going to show the paths of all the optimizers. Alright, so let's implement it. First of all, we make sure that paths, colors, and names have the same length because they correspond to the same set of optimizers. We compute the maximum path length across the different optimizers. However, in our example, all of them will have the same length. We prepare a grid of x and y coordinates, and then we evaluate the Rosenbrock function at all of them. Here we just save the x and y coordinates of the global minimum because we know what it is and we want to visualize it. We create a figure and then we create a contour plot of our Rosenbrock function. We predefine a scatter plot for each optimizer. We plot a legend, and we also plot the coordinates of the global minimum. We define a function called animate, and we will use it to generate different frames of our animation. And finally, we create a func animation object providing our animate function, our figure, and other parameters influencing how the final animation is going to look like. All right, so now we wrote all the boilerplate code and we can test whether it works. First of all, we specify the initial x and y coordinates. We are going to run the optimizer for 1000 steps. We run two different optimizations. The first is going to be using the Adam optimizer, and the second one is going to be using a vanilla SGD, stochastic gradient descent. Here I define the frequency for the final animation, and the idea is that we don't necessarily want to have 1000 frames, and instead we want to take every 10th frame. And finally, I prepare all the inputs for the create animation function and I run it. The last step is to save the animation as a GIF on our computer. All right, and now we can try to run it. We can see that both of the optimizers go directly to the value, and once they are in there, they just continue towards the global minimum. Let us now implement a custom optimizer. Just for the record, we're not trying to beat the state of the art or whatever. The goal is to show some features of the optimizer class and how you can use them. Alright, so here we import NumPy and Torch and the parent class optimizer that we will need to subclass. We name our optimizer weird descent, and the way it behaves is very similar to the coordinate descent algorithm. However, in our case, we're going to choose the coordinate randomly and not necessarily cycle through all the coordinates. Additionally, with every 100 step, we will multiply the learning rate by a very big constant. The only hyperparameter that this optimizer is going to have is a learning rate. And what we do, we insert it into a defaults dictionary, and then we use it to call the constructor of the parent. We're not going to use the concept of a closure in our example. However, you might want to use it when you need to evaluate your loss function multiple times, and some existing optimizers are actually using this. Here we want to define a key step inside of our state dictionary. And if it's the first step, we set it equal to 1. And if it's any consecutive step, we just keep on incrementing it. We need to keep track of the number of steps in order to be able to recognize whether the current step is a multiple of 100. So if we happen to be in a step 100, 200, 300, and so on, we just define C to be something really big, for example, 100. Otherwise, we keep it equal to 1. Let me explain what this block is trying to do. First, we want to randomly select a group out of all the available parameter groups. Given this parameter group, we then want to select a random tensor that belongs to this group. Once we have this random tensor, we try to access its gradient. If it's defined, great. If it's not defined, we repeat the above process until we hit a tensor that has gradients computed on it. Also, let me point out that in our example with the Rosenbrock function, we will only have one parameter group, and inside of this parameter group, we will only have a single tensor. Given our selected tensor, we want to pick one element at random. Once we have our element, we will create a masked tensor that will have the same shape as our input tensor, and it will be equal to zeros everywhere except for one entry. Finally, we perform the parameter update. The way we do it is by taking the gradient tensor and the mask tensor and multiplying them element-wise. What this will essentially result in is an update only along one single coordinate. The alpha parameter defines the multiplier we are going to multiply the update with. As you can see, we take the learning rate and also our constant. Finally, we return the loss. Alright, so let's test out our optimizer. I just directly modified our source script to include the weird descent optimizer. And also at the end, I'm printing a few rows from the path array. It is always just one coordinate that is changing its value at a time. As you can see, our optimizer is jumping every 100 steps, which is something we expected. And when it comes to moving along a single coordinate at a time, unfortunately, we cannot see it clearly in this animation. The reason for this is that we only show every 10th frame. Anyway, that's it for the video. I hope I managed to cover the most important things. And if you're interested in the topic, I would definitely encourage you to read through the official PyTorch source code, documentation, or even look for implementations of custom optimizers in third-party packages. Thank you very much for watching and see you next time.